Good afternoon, everybody. Welcome back to the season 3 of our online seminar series, Machine Learning Needs Mathematical Optimization. We have the pleasure today of having Peter Richtarik, who is a professor of computer science at the King Abdullah University of Science and Technology. And he is the leader of the Optimization and Machine Learning lab over there. So Peter is actually a founding member and a fellow of the Alan Turing Institute in the United Kingdom, and he is also an EPSRC fellow in mathematical sciences. So prior to joining his current affiliation, he was an associate professor of mathematics at the University of Edinburgh. He has also been a postdoctoral researcher and a visiting researcher at Université Catholique of Leuven in Belgium and University of California, Berkeley in the USA. He has received a PhD from Cornell University. He is very at the topic in this online seminar series because his research is at the intersection of mathematics, computer science, machine learning, optimization, numerical, linear algebra, and high performance of computing. And his work has appeared in leading journals in our areas such as mathematical programming and SciAm Journal on optimization. And he has received many prizes also. Peter has ample experience in editorial work, and he is the area chair for leading machine learning conferences such as ICML, and he is also an area editor for the Journal of Optimization Theory and Applications. So we are very pleased to have you today here, Peter. The floor is yours, and for the audience, remember that Peter is happy to take questions as he goes with his presentation. And if you want to post them in the chat, I will also be happy to monitor that and read them for Peter. Thank you so much again, and please go ahead.
Thank you very much for the very kind introduction. It's really great pleasure to be speaking here today. So I definitely am a believer in the name of the seminar series, Machine Learning Needs Mathematical Optimization. So this is something that in my group we're doing every day. So we work at the intersection of mathematical optimization and machine learning. And today I'll speak about one paper, which is an optimization paper. So it's a paper about an optimization algorithm. But this paper was accepted just recently. In fact, on the same day that this seminar was announced on social media at the leading AI conference, which is the iClear conference, International Conference on Learning Representation. So this is one example of intersection between optimization and machine learning. There are, of course, many papers which advance optimization appear in machine learning and AI conferences and vice versa. And in particular, I'll talk about so-called permutation compressors. So this is something that is new that we propose in this paper. So if you've never heard of compressors and distributed training, I'll explain what that means. And permutation compressors is a new class of compressors which in some sense are better than what was there in existence before. So that is really the key behind this work. This is joint work with two very talented young people, Rafał Slendak, who was an intern in my team last summer here at KAUST, and he's a student at Warwick in the UK, and Alexander Turin, who's a postdoc in my team. And this paper has been on arXiv since I think October last year, and as I said, it was recently accepted to this conference. Let me first introduce the problem here. The problem that we work on our team quite heavily, not exclusively, but I would say quite heavily, is this seemingly very simple looking problem. And the problem is minimize the average of n functions in the variables. Okay, so the difficulty here comes from three sources. One source is the number of functions, n, then that could be very big. Then the number of variables or model parameters, features in machine learning, which could be very big. So this could be billions, and n could be thousands or millions. And then structure of these functions, fi's, which may come from neural networks. These be loss functions over some training data sets stored across these n devices. And the structure of the neural network may dictate that this loss function can be highly non-convex, and because of this difficult. So in this talk, this finite sum minimization formalism actually means that n is the number of machines or devices or clients or nodes or workers that want to jointly minimize the average of these functions. So really the motivation here is coming from supervised machine learning, where there is a machine learning model or statistical model, such as a neural network, which is parameterized by d parameters. As I said, d is huge. And what we want to do, we want to find the model x parameterized. So these parameters parameterize that model, which minimizes the average risk or average empirical loss across all of these n devices. So that is really the problem here. So how do we do that? So the key difficulty here, out of the difficulties I already mentioned, is the fact that these data sets and these loss functions are distributed across n devices. And these devices are connected through some links, so maybe just through the internet, and they can communicate only very, in a very difficult way. So maybe there's a server that all of these clients can communicate with, and this is how they can collaborate when solving the problem. So here on this picture, you would see a situation with just 3 devices. So here everything is very small, and we want to minimize the average of 3 functions. And these devices cannot communicate among each other directly, but only through some weak links and the server. So this is a situation very common in a new paradigm of machine learning called federated learning. And these devices could be mobile phones, laptops, and so on and so forth. So this first device here, laptop, has some training data set D1, and the training data set gives rise to a local loss function F1, which depends on the data set. Client 2 has training data set D2, could be of different size, different parameters, different dimensions, and so on. And this loss function is F2, and so on. So this is roughly what's going on. And the key bottleneck here is the communication cost. And this is why I'm talking about compressors in this work. We would like to handle the communication cost by compressing the communication. And then through compressing communication, we hope we can get an algorithm which would be faster, would be able to work with weak communication links, and which might be even better if we didn't compress communication. So this is the surprising observation through the recent literature on this topic, that by compressing communication in a lossy way, so that you're actually not communicating what you really want to be communicating, the overall algorithm will be mathematically better and practically better. Okay, so I want to right away explain what assumptions I'm going to assume on these functions so that everything is mathematically defined. So I'm going to assume that these functions fi, these local loss functions, local to the clients, they have Lipschitz gradients with some Lipschitz constants Li. So this is a very weak assumption, I would say. So we assume differentiability and something a little bit beyond Lipschitzness of the gradients. And then I only have a second assumption, and that's it. I have no other assumption on these functions whatsoever, no hidden assumptions. So the average of these loss functions is lower bounded, which makes sense. If you want to minimize the average, it's a good thing to assume that the minimum is not going to be minus infinity. So this is really everything. So this is a non-convex distributed optimization problem. And our goal, since the problem is non-convex, we're throwing away any hopes of finding a global solution. Instead, what we want to find is a point which is stationary approximately in this way. So we allow for the algorithm to be tossing coins. So we allow the algorithm to be randomized, and this is why there's an expectation, and the output could be a random vector x. If the algorithm is deterministic, then you can throw away the expectation. So we want to find a random, possibly random vector x. So this will represent the model such that the gradient of the function that we want to minimize is small in expectation. So that is really the goal. And on top of it, we want to do this with minimal communication, and this is what is special about the setup of distributed training. So communication is really the key bottleneck. The local computation, we assume, is not a problem. So you can do kind of whatever you want locally on these machines because they will be pretty fast. But once you decide to communicate something with your peers, because you need to do that because none of the clients contains all the data to be able to solve the problem alone. So they need to communicate somehow to jointly solve the problem. We assume that that is really the main cost. So in fact, we'll be counting the efficiency of algorithms in terms of the number of communicated bits necessary or sufficient to solve the problem. So this is, and we'll be only counting the bits which go from the devices to the orchestrating server, because this is typically the bottleneck. Okay, so there are many other issues in distributed training in general, and federated learning as an example of distributed training in particular, such as partial participation of devices. So that's a paradigm where you want to say that if you want to train over millions of devices, so you want to minimize the average of 1 million functions, then maybe these million devices are not always available in every communication round, so you may need to work with maybe just a few thousands in every communication round. So we're going to ignore this completely. We're going to ignore stochastic approximation as well. So many times in practice, what you want to do when you compute gradient information on devices, so gradient of Fi, you may wish to just approximate it through some mini batching procedure because the device may contain so much data that computing the full gradient is prohibitively expensive. We're going to ignore this as well. We're going to ignore the paradigm of local computation where each device might want to take multiple steps of some local algorithm before communication, and we're going to ignore differential privacy concerns, which are important in federated learning. So we'll purely focus on communication compression and what can we do in that space. Now, our techniques can be combinable and combined with these other techniques, but this is just beyond the scope of this work and also this talk. So the starting point really of our research is this work of Gorbunov and co-authors on the MARINA algorithm, which at the moment is the state-of-the-art algorithm for non-convex distributed training in terms of communication complexity. So it's an algorithm that works as follows. So you have the current model xt, and you subtract in each communication run from it a multiple of some vector gt, which is the average of some vectors gits produced by these devices. So remember, we have n devices and clients, and git is the vector produced by device I and sent to the orchestrating server. So the server sees all of these vectors git, can average them, and can subtract a multiple of this average from the current model xt, and then the model xt plus 1 is broadcast to all the devices, and this process is repeated. So MARINA is a special case of this very generic method, because I didn't tell you how GITs are defined. So that this can, in fact, this formula here can encode any method, any iterative method, so we need to really specify this. And the GIT is defined in MARINA in the following way. So there is a coin on each device, and with some small, very small probability p, the client I, can you see my my arrow, mouse pointer here? I'm trying to make a circle around.
Not at the moment.
Okay.
Not at the moment.
So I won't be using this then. Okay. So with some very small probability p, client I computes the full gradient of the local function fi. So you can see gradient of fi at point xt plus 1, which is the latest iterate. So this could be, and this is then sent to the server. So remember that this gradient Fi is d-dimensional, and d could be billion. So you're sending 32 times billion bits to the server, and that could be really, really huge file just in one communication round. But this happens with very small probability. And with very high probability, 1 minus p, you're going to send this gt plus ci, and ci is this operator applied to the difference of two consecutive local gradients. So vector you don't actually send. So by the way, I can hear somebody typing, so maybe if somebody can mute themselves would be easier. So this GT vector is not sent to the orchestrating server because GT is known by the server from previous iteration. So all that you do with this high probability 1 minus p, you just compress through CI the difference of these two gradients and send it. And this compression can be lossy, and there's a mathematical definition of what this compression means. You can see it in the bottom left corner. So it has to be some mapping from RD to RD, which is possibly randomized, which on expectation outputs the input vector. So if you want to send V, you're going to, on expectation, get V. So expectation of CI of V is V. So this makes sense because you want the approximation of this difference to be on average correct. And then if you look at the second defining inequality, so that bounds the variance of compression. So V is what you want to compress, CIV is the compressed vector, so expectation of the square difference is the variance, and this is upper bounded by some multiple, omega I, of the square norm of the input vector V. So this is a classical class of compression mechanisms, which includes many, many examples. I will give you one or two very soon, and we will work in this level of generality here. So this is the algorithm, and maybe I'll pause here for a second in case there are some questions, and in fact, I would quite appreciate if there was a question or two before I move on. And the reason for that is I will talk about an improvement of this algorithm. So if there are any doubts about what this algorithm is doing, please ask. I don't really have time to go into details in explaining what this algorithm is doing, but on an intuitive level, I'm happy to answer any kind of a question. Of course, later on, I will show analysis of an improved version of this method. And if you don't mind, I'll just wait for a minute until I get a question. So is there a hero who will interrupt the silence and ask a question? All right, I waited long enough now, so I'll move on. I'm assuming that you're happy with the description so far, but please do not hesitate to interrupt me at any time. I actually like talking to people rather than listening to my own voice, and I like to have a discussion when I give talks. So please, please, please interrupt. I actively want you to interrupt me. Okay.
Peter?
So,
Peter?
yeah. Very good. Somebody's
yeah, exactly. So, Nagisa, would you like to ask the question, or would you like me to read it? I think you can unmute.
Hello, can you hear me?
Yeah, I can hear you.
Thanks. My question is very kind of basic question, but I was wondering, this probability P we can choose arbitrarily, and if so, like, is there any way to choose or like actually optimize it or something like that?
Yes, yes. So the algorithm, this is a very good question. The algorithm has a theoretical guarantee for any choice of this probability, any choice except 0. So the probability cannot be 0. It has to be positive, but could be arbitrarily small. And with any choice of this probability, I can bound the number of iterations, so I can have an iteration complexity result. And the number of iterations is equal to the number of communications. But then when you look at the result, you may wish to optimize this over the probability. And that is why I'm saying that the probability should be very small, because when you do the optimization, it turns out that P should actually be very small. And this will be maybe a little bit clear later on, but somehow the probability should depend also on the properties of the compressor. If the compressor compresses a lot, then the probability should be different than if the compressor doesn't compress much. So there's a connection to that too. But the takeaway message should be, there's 3 takeaway messages. The algorithm works with any choice of the probability as long as it's positive. But some probabilities are better than others, and the probability should depend on the choice of the compressor. And I'll give some more comments on this later.
Okay.
Okay, good. So I'm moving on, and now I want to focus. Yeah, there's another question. Yeah.
Yes.
Please.
Yes.
Now
so the question is whether C is random.
Whether CI is random. Yes, so CI, the compressor, will be random. And I'll give an example very soon of a random compressor. And I want this to be unbiased estimator of the input. So any kind of a transformation which on average outputs the input and has as small variance as possible. So I'll get right to it right now, because I'm going to introduce some compression operators just for you to understand a little bit more about these CIs. So that's exactly what I'm going to talk about next. So one thing to understand here is that the server will want to eventually average some compressed vectors. Okay, so these compressed vectors are sent to the server, and the server will want to average them. So this is some kind of a subroutine that happens in this algorithm. And now this is the average of the uncompressed vectors, this is the average of the compressed vectors, and in some sense these are the compressors, and in some sense we want the average of the compressed vectors to be as good an approximation of the average of the uncompressed vectors. Okay, so that's some abstract understanding of what's happening in these methods which compress communication. And since this is a lossy compression, there won't be an equality sign. So this is not lossless compression where you just go down with the bits, but you don't lose any information. You actually lose information. You may lose it really, really heavily. So for this class of compressors which are unbiased and have this variance bounded by omega I times this norm squared, we'll have this notation for it that is this U omega I class. So you may see it every now and then. Okay, so now the question is, what do we mean by this approximation? So there are roughly two design principles. One of them is the prevalent one, and the other one is new, which we introduced in this paper. So current literature designs these compressors individually. So compressor CI is used on device I, and it's used independently from what the other devices do. And that makes a lot of sense, because these devices cannot communicate easily, only through the server. So somehow the compression has to be done independently from the compression on the other devices. So this makes a lot of sense. But we want to break this limitation, and I'll explain why. And we propose here an approach where this compression is done jointly, but very efficiently and cheaply, so that these devices don't really have to communicate much to decide on how to compress. And we say that by joint design of these compressors, we can gain a lot. So that's somehow an abstract understanding of what's happening in this work. Now I want to focus a little bit on this current literature and give you an example of compressor. So there's roughly two classes of these compressors based on the idea of sparsification and quantization. So sparsification means that out of this d-dimensional vector, you zero out many entries, and you only keep k entries. Okay. So if you do that, then you get compression ratio D over K. So if let's say K is 1, then the compression factor is D over 1. If D is million, this is 1,000,000 times compression. Quantization, on the other hand, doesn't sparsify, but the idea that instead of representing every float, every entry of these D entries of the vector using 32 bits, you represent that float using B bits, where B could be much smaller than 32, such as 9 or 6 or something like this. And then the compression ratio that you get is 32 divided by B. I won't talk about quantization, I'll only talk about sparsification. So let me talk about the simplest possible sparsification routine, which is called the random K compressor. So here's an example of a D-dimensional vector, which is, of course, not something that we practically are interested in. And this is the local gradient vector that device I wants to be sending to the master. So let's say that D is huge. In this case, D is 5. So we don't want to send this 5-dimensional vector. We want to only send 1-dimensional vector. So capital K is 1. So what this random 1 sparsification operator actually does, it picks a random entry out of these 5 entries. It happens to be the third entry, number 2, and zeroes out everything else, and then multiplies the vector by 5, because when you do that, then this random vector is unbiased estimator of the input vector on the left. So this type of mechanism actually satisfies these inequalities, identities on the upper right, and omega I just happens to be exactly 5 minus 1, which is 4. So dimension minus 1 in this case. So if you run this compressor another time on the same input, you may get a different output because it's a randomized compressor, because you always flip a coin with probability of the first entry being selected being 1 over 5, second entry 1 over 5, and so on. So in this case, the last entry was selected. You also multiply by 5, and that's the output. Or maybe the first entry would be output. So there's 5 possible outputs for this type of a compressor, random 1. But always omega I is dimension minus 1, in this case 4. So this is the simplest sparsification compressor. And you can see that the reduction in communication is exactly equal to the number of dimensions. So you go from 1,000,000-dimensional vector, if D is 1,000,000, to 1-dimensional vector, because you only need to send this one entry and its index, and you don't have to send the zeros. Okay, so this is the most famous example of a sparsification operator. And now I'll say something about this joint design of compression operators and why we would be interested in something like this. So there is a key weakness of this independent design of compressors, and the key weakness is that they do very badly when they aggregate similar vectors. So imagine that we have 3 machines now, so 3 clients, so n is equal to 3, and we want to average these 3-dimensional vectors. So D is also 3, dimension 3. So of course, D dimensions are very small because I want to show you a picture. And assume that these vectors that we want to average are so similar, in fact, they're identical. So this is the extreme case of similarity, they're the same. What would happen if you use this random 1 compressor on each client? So these vectors get replaced by the compressed versions, and the compressed versions is simply pick 1 entry, zero out the rest, and multiply by dimension, by 3. So this is the possible output of these independent compressors applied, random 1 compressors applied on these devices, okay? So notice that the first machine keeps the first entry, the second machine, the second entry, and the last machine also the second entry, because this choice is random. Now notice that in this case, when you average the compressed vectors, you get the vector 4 minus 14, 0, which is different than the average of the actual vectors, which happens to be 4 minus 7, 2, because all the vectors are the same. And this seems to be very strange, because this seems to be a very simple situation, right? So all of these vectors we wanted to average are exactly the same. So why on earth are we sparsifying in the silly way that the first machine sends the first entry, second machine second, and the third machine second as well? So the simplest possible idea how to improve this would be, in this regime of identical vectors, would be design these compressors jointly. So let not the machines choose this entry to keep independently of the others, but let them collaborate. So for instance, first machine would pick the first entry, second machine the third, and the last machine the second, so that in fact these indices of these elements that are kept, so 1, 3, 2, this is actually permutation of all the indices 1, 2, 3. In other words, each machine sends a different entry. Since there are 3 machines and 3 entries, if each machine sends a different entry, then the average of these compressed vectors will be exactly recovering the average of the uncompressed vectors. In other words, the average of the compressed vectors in this way, using this permutation type compressor, will be 4 minus 7, 2, and the average of the uncompressed vectors is also 4 minus 7, 2. So this permutation way of sparsifying and compressing leads to much smaller variance in case when these vectors that we're going to average are identical. Okay, so this is all just intuition, and now the question is, how can we kind of formalize all of this into some sort of an abstraction? So the idea, the new concept that we introduced in this work is called the B Inequality. So we want to jointly design these compressors, so we need some property that is jointly satisfied by all of these compressors. And this is the inequality. So notice that we have these n input vectors. So we have n machines. Machine I contains vector vi. All of them are d-dimensional. And what we really want to do, we want to compute the average of these vectors, but they are all dense and d-dimensional, so we'll compress each of them and compute average of the compressed vectors. So the left-hand side of this inequality is nothing else than the variance of this random vector, which is the average of the compressed vectors. And we want to upper bound the variance, and this is new in this paper, so such an inequality didn't appear in the literature before. We want to upper bound it by a multiple a of essentially the average of the squared norms minus multiple b of the square norm of the average. So it turns out that this is the right inequality in this context. So these are the compressors, n is the number of clients, and these are some parameters which will define this collection of compressors. Okay, so now this may look mysterious, but let me add some insight into this. So first of all, first observation is if this inequality holds, then this inequality must hold. So if C is the average of the CIs as a mapping from RD to RD, then its variance when applied to some vector V is upper bounded by A minus B times the input vector V and its norm squared. This actually means as a corollary that A has to be at least B, because the left-hand side is non-negative, and the right-hand side would not be non-negative if A was smaller than B. So in fact, A has to be at least B. So going back to this inequality necessarily implies, if it holds, that A is at least B. So now there's this question, what happens if A is equal to B? Can we actually design compressors which satisfy this inequality with A is equal to B? So if such compressors exist, we'll call them input variance compressors. The reason for that being, if you rewrite the right-hand side of this inequality, and this is not a new right-hand side, I'm just rewriting the right-hand side, and I'm calling C the constant A. A is equal to B, and I'm just calling them C. So the right-hand side just turns out to be the variance of these input vectors V1 through Vn. So this collection of compressors is called input variance compressors because the variance of the average of the compressed vectors is upper bounded. So that's the left-hand side. It's upper bounded by a multiple of the variance of the uncompressed vectors. Okay, so that's and these uncompressed vectors, these are the input vectors, so the variance of the input vectors actually matters. And now this connects to this intuition of permutation compressors. So in that case, I mentioned the definition of a permutation compressor on an example where all of these vectors, V1, V2, and V3, remember we had 3 vectors of 3-dimensionality, of 3 dimensions, they were identical. So if you have identical vectors, the variance is exactly 0, right? So if we could, in general, design input variance compressors that if we were compressing identical vectors, then the variance of these input variance compressors would always, on identical vectors, be 0. So this permutation trig was just one example of an input variance compressor. So let me pause again, and I would very much welcome some questions. Okay, so if you think of some questions, please don't hesitate to interrupt me, and I'll just keep going. So at least we got a little break here. And now there are many examples in the literature of compressors, which we can then show they belong to this category of compressors satisfying the AB inequality. So many existing compressors can be shown to satisfy this inequality, but they were never analyzed as such. So this joint property of these compressors was never a part of analysis of some optimization algorithm. And here are just some examples. So for instance, the permutation compressor, which is in this third line and the fourth line here, it turns out to be input variance compressor because if D is at least n, we have a specific definition of permutation compressor, definition 2, and constants A and B are equal to 1. And remember, if A is equal to B, as we call it C, we get an input variance compressor. If D is less than or equal to n, we need to define the permutation compressor in a slightly different way, and then A is still equal to B, but they're both actually smaller than 1. So permutation compressor is a special case of this general definition of an input variance compressor. Okay, so now there's a fourth piece of the puzzle to this improvement I'm going to talk about, which is, again, a new notion, something that we call Hessian variance. So let me explain what I mean. So in non-convex optimization, there are certain smoothness parameters that typically play a role in the analysis of algorithms. So the simplest of them is just the bound on the gradient differences, so which is just the Lipschitzness of the gradient. Okay, so if this inequality holds for every x and y, you say that the gradient of fi of this localhost function is Li Lipschitz. But I want to call this bound on the gradient differences. So you can also create a bound on the second moment of gradient differences. So you average these things on the left-hand side, and you upper bound it by some other constant multiple of x minus y squared, and this multiple we just call L plus. So this is a new smoothness constant, L plus. Since we have second moment, we can also think about the mean of gradient differences. So we have this left-hand side is the mean of gradient differences, and the smoothness constant would be L minus in this case. So the first is very standard. Second is already very non-standard. In only very few papers, you see this constant L plus, and the last one, this is completely standard because average of fi's is simply f. So this is simply L minus is just Lipschitz constant of the gradient of f. Okay, so the first and third are quite standard. The second is a little bit non-standard. It turns out these notions are connected. So for example, if the first inequality is satisfied, then the second one is satisfied because you have always this inequality that L plus squared is upper bounded by the average of the Li squares. If the first, yeah?
There is a question. So when you are finished with the slide, then yeah.
No, I'm quite happy to take it right away.
Frank, would you like to unmute and pose your question? Apologies, it's only because the slides are not moving at the same pace as your explanation. That's
okay, so there was just comment that...
more than a question. Yeah.
Yes, I do not know how to control this, unfortunately. So what do you recommend that I do to fix it?
I think we will pay attention to it, and then I will stop you. Yeah.
Okay, so this is issue, I guess, with the system because normally this doesn't happen with something like Zoom. So I apologize for this, but I don't think it's anybody's fault. here. We just have to.
Yeah, no, not at
okay,
all.
so
yeah, thank you. I will pay.
Okay. So I'll continue with the slide. So inequality 1 implies inequality 3 as well, because this L minus constant is always upper bounded by the average of the Li's, and it turns out second inequality implies the third, because L minus is upper bounded by L plus, which is why we chose the notation L minus and L plus in the first place, to indicate that L minus is smaller than the L plus. Okay, but it turns out that for the analysis of this algorithm, there's a new smoothness parameter which was never analyzed or proposed in any literature, is needed, and it plays a very important role. We call it Hessian variance, and it's actually a bound on the variance of gradient differences. So remember, we had second moment, first moment, and so on and so forth, but now we have the variance of gradient differences. So this looks a little bit complicated, but on the left-hand side, you just have variance of gradient differences, and on the right-hand side, you have just multiple of x minus 1 y squared. And we call this constant L plus minus. And we call it L plus minus for a reason which I'll explain soon. So why is this variance of gradient differences? Because this is actually expectation of something like this. So this is a variance of random vector v when the random vector v is defined to be vi with probably 1 over n, and vi just happens to be the difference of the gradients of fi at x and y. So that's why I call this variance of gradient differences. So together we have these 4 inequalities, and the fourth one is implied always by 2. So it's always smaller than L plus, and it's L plus minus because in fact it relates to L minus as well, but it's not shown here. Okay, so now it turns out, and this is really the key. Notice the fourth inequality. So L plus minus is always upper bounded by L plus, but unlike these other 3 constants, which in some sense are always very large, L plus minus can actually be very small even for difficult problems. So let's see why. So if you have functions which are all identical, so that's the first row in this table, then the Hessian variance is just 0. Okay, even if the functions are difficult, the Hessian variance is 0. If they're identical and you add any linear function to them, and they can be arbitrarily different linear functions, which in particular means that the minimizers of these functions fi could be arbitrarily different, the Hessian variance is also 0. If you have quadratic functions with Hessian ai on arbitrarily linear parts, then the Hessian variance is nothing else than the largest eigenvalue of the variance of the Hessian matrices. So you can see that the lambda max, the largest eigenvalue, takes an input, something that can be interpreted as variance of Hessian matrices. And in general, if you have twice continuously differentiable functions, then there's a closed form formula for Hessian variance, which is shown here. So this is a closed form formula, and there's some expression for this L plus minus 1 function, and it can be interpreted as variance of some average Hessians, and average Hessian is the integrated Hessian from x to y of fi. So let's not spend too much time on this. And we have a theorem which says what all of these L minus, L plus, Li, and L plus minus is in case of general twice continuously differential functions, but that's not important. Okay, so now I explained this notion of Hessian variance, which at this moment should be a little mysterious because it's just not a standard notion. But let me now explain why it's important. So it's important because of this theorem which we proved, and this is a new proof for the algorithm MARINA, but it's a generalization of the proof from the MARINA paper of Gorbunov and co-authors, because they only worked with these independent compressors, and we work with any compressors which satisfy the AB inequality, which means that they can be dependent in any kind of a way. In particular, they can be dependent through this permutation idea. So we generalize the results of MARINA, which work with independent compression mechanisms, to arbitrary dependent structures. And the constants A and B, they distill the dependency of these compressors. And we have this general theorem which says, if the number of iterations is at least something like 1 over epsilon, And it's not the one is twice the function suboptimality. So fx0, x0 is the first model, the first iterate, and finf is just lower bound on the function, times this big expression in the parentheses. Then we have solved our problem. So I explained that we're looking at a random vector who's such that the gradient of f evaluated at this random vector is small. So if the number of iterations is at least some constant divided by epsilon, we have found an epsilon stationary point. And notice that these three parameters, the green, let's say orange or reddish, and the blue one, L plus minus, they play a role in this complexity. So not the yellow one. And the probability P plays a role as well. So there was a question, how does P play a role? It's there in the square root. Okay. Now notice that the constants A and B, which characterize the compressors, they enter this complexity as A minus B multiplied by L plus, and L plus, remember, is the largest of all of these constants. So that's the big one. And B is multiplied by L plus minus. And remember, this is the Hessian variance, which could be actually very, very, very small, even for very heterogeneous data. So now what does this mean? This means that, in particular, if we work with input variance compressors, so these are the compressors where A is equal to B, then we can completely get rid of dependence on L plus, which is the bad constant. Okay, so that's a very important first observation. And previous work was unable to do this because they worked with independent compressors, and independent compressors can never have A equal to B. And if you work with low Hessian variance regime, if this blue constant here, L plus minus, is small, then you remove also that dependence on B. And in some sense, if the Hessian variance is actually zero completely, if you're very lucky, then this whole square root is gone, it's zero. Okay, so again, if you are in zero Hessian variance regime, which is the best possible regime you could be in, and you use input variance compressor, which means A is equal to B, then the square root is zero. And that means you get a rate, which is just L minus times 2 times function suboptimality divided by epsilon. That's it. As simple as this. This is exactly the rate of gradient descent in the non-convex regime. But notice that gradient descent needs to send full d-dimensional vectors to the server in each iteration, whereas this method only sends, if you use the perm1 compressor, only sends one entry of the d-dimensional vector. So if d is million, this is million times faster algorithm in terms of communication complexity than gradient descent. In the best case, on Hessian variance is zero. Okay, so this input variance compressors, they really remove the dependence on L plus completely. And if Hessian variance just happens to be small, using input variance compressors really helps. So this is really the main message. So I'll mention this slide just to characterize this numerically a little bit. So if we use the random one compressor of Gorbunov and Carter's, then this AB inequality is satisfied with B is equal to 0, but A is not 0. It's D minus 1 over N, where D is the number of parameters, N is the number of machines. And this constant, which appears in the complexity, which is in this red box upper right, just happens to be D minus 1 over N times L plus squared. In our work, A and B is equal to 1 with permutation compressor, and the constant is just L plus minus. And if L plus minus is very, very small, and it's definitely smaller than N plus, then we can win. And this is always an improvement on the previous result. And in fact, so this slide I want to skip, but I want to just focus on this bottoms of the slide. So if the number of parameters is bigger than the number of machines that you have, so if you are in the big model regime, then this is up to square root of N improvement on communication complexity of MARINA, which was up to now the state-of-the-art method. And N could be thousands or millions in federated learning. So this would be 1,000 times speed up in communication complexity. If you have many more machines than the number of parameters, which happens in federated learning quite a bit, then this is up to D over square root of N improvement on MARINA, on using these independent compressors. So again, I'll pause here because I only have one last part and only a few slides on experiments. So I'll stop here and I'll welcome any questions on this theoretical part. And maybe I'll just go to the main theorem as I'm waiting for questions. And as I'm waiting, I'll just say that the reason why we introduced this AB inequality and the Hessian variance, so the new concept, is just because that's exactly what shows up in this analysis. So somehow, as we're doing the analysis, that turns out to be the important concept. And you can see how the interplay of the compression and this Hessian variance really plays a role in this analysis, and why input variance compressors are really important, because they completely get rid of dependence on L+, which is really huge. And if you are lucky and you're in this low Hessian variance regime, then you can completely get rid of this square root, and then everything just becomes really, really good. So if you don't mind, I'll just wait for 1 or 2 questions, and then I'll move to experiments.
Hello, can you hear me?
Yes, I can hear you.
Thanks. My question is, I want to understand where this improvement came from compared with the a random a compression. And I was thinking, is this a improvement coming from a low variance, as you explained? If the function is very simple, the permutation is much low variance. Actually, it's zero. Kind of intuition.
So yes, the intuition is that the traditional approach of compressing the vectors is that these machines, they don't collaborate, so to speak, when they compress. So everybody does it independently. But if you insert smart dependence, and this permutation is a very, very cheap way of inserting smart dependence, then the variance of the average of the compressed vectors just becomes much, much smaller than without this correlation. And that really drives the convergence. Okay, that really improves things. And in particular, if the vector is identical, the variance will be 0, right? So that was the motivation of the permutation compressors. But even if you are in a not really low variance regime of the original input vectors, this is an improvement. Really, it comes from the dependence, smart dependence between the compressors. If they're independent, we don't get that improvement, and we just recover exactly the analysis of MARINA from the original MARINA paper. But with the smart dependence, we can choose compressors where A is equal to B, and then we completely get rid of dependence on L+, and that comes from smart correlation.
So my kind of second quick question is there any kind of function where this L+- is getting large and there's no improvement compared with MARINA?
So there's always improvement on MARINA. So only in the worst case, we recover MARINA rate. So this is never worse than MARINA. Never. So there's no regime when this is worse. It's always better. So something you can think of it that in the worst case, we get MARINA, and we can get much better. So this is never worse.
Thank you.
And the reason is because in MARINA, in the original MARINA, B is 0, so there's no dependence on L+-, okay? And instead of A minus B, you just have A, because B is 0. So there's always A times L+ squared. But A is always bigger than B, and L+ is always bigger than L+-, right? So by pushing weight from L+ to L+- is always good. Okay, and with input variance compressors, you can push all the weight from N plus to L plus minus, because you can just zero out the weight in front of L plus and push it essentially all to L plus minus. So that's where this is coming from.
Thanks for clarification.
My pleasure.
Peter, yeah, a kind of a comment on the chat. I will read it, but I think it's more a comment. So it says that take a subsequence that converges weakly and hope that it works. Unfortunately, weak convergence and independence are not married. Yeah, so.
So I don't have any result here on convergence of some subsequence. So as you see, this is convergence in expectation. So this is an iteration complexity result, which is stronger than some sort of convergence of some subsequence. And once you have a result of this type, you can always use a marker of inequality, get the result in high probability. So I think this comes from some misunderstanding of the notion of convergence that we use here.
Thank you so much, Peter.
Okay, so do I still have these 5 minutes because we started late, or should I just stop now?
Oh, yes, please. No, go ahead with your 5 minutes.
Because I'm quite happy to stop if the time is up, but I do have a few slides on experiments, so if that is
we would love to see them. Yes.
Okay, good. So the theory now leads to this new state-of-the-art theory for distributed training in terms of communication complexity in the non-convex smooth regime, as I explained. Let's see whether this theory actually translates into any improvements in experiments, because theory does not necessarily have to be tight in general, and good theory doesn't have to mean that the practice is good, right? So we're always very interested in seeing whether these ideas also work in practice. So we first started with some synthetic non-convex quadratics, just to see in some kind of a synthetic environment or lab environment whether these ideas work. And we use 1,000 clients, 1,000 features. This is what the quadratics look like. And we first introduced zero Hessian variance. So we generated this problem in such a way that the Hessian variance was exactly zero, which essentially means that the AI matrix is shared among all these clients, but the BI vectors could be arbitrarily different. So here we run the method. So you can see on the x-axis the communicated bits per client. So 1 means times 100, I think, million, right? So this is 100 million. So 1 means 100 million communicated bits per client. When you do that, then you can push the gradient below 10 to the power minus 7 or 10 to the power minus 8. And as you can see, the permutation compressor is the best from these two benchmarks. The natural benchmark is the red line with random K, so the random approach, so that is worse. And the blue benchmark is the top K compressor. For this, we actually had to run a different method because top K compressor is a greedy compressor, is not randomized. And typically, this is very good in practice, but is very not understood in theory. So the top K compressor theory is worse than gradient descent by a lot. And permutation K compressor is by a lot better than gradient descent. And even random K is by a lot better than gradient descent. But top K, nevertheless, even though the theory is very weak, the Besnel theory is very weak, it does really well in practice. So we wanted to compare against that too. And in this case, it beats also top K. So by something like 2 orders of magnitude. So this is all very encouraging. But of course, we are in the best possible regimes. That is the homogeneous data regime where Hessian variance plays to our cards. It's the best possible Hessian variance we can think of. So this was the experiment that I highlighted, and notice L plus minus was 0. Now we started increasing Hessian variance, so from to 0.05, 0.1, 0.21, and so on. And as we do that, we make our life for the MARINA method with permutation compressor harder. And if you pay attention to these plots, you would just see that the gap between permutation K and top K just starts closing, and at some point they become all quite similar because the Hessian variance is just quite large at that point. So now we tried to train an autoencoder with the MNIST dataset. So this is actually what the problem looks like. It's a non-convex problem because you can see that these decision variables D and E, decoder and encoder, they here appear in multiplication as a product. And so let's not spend too much time on trying to understand what this actually means, but it's a non-convex problem of canonical importance in machine learning. So now if we partition the data randomly, which kind of represents homogeneous data partition, which kind of means that the Hessian variance should really be small. And if you see what's going on, then permutation compressor does best. It does, but top K is pretty good, and random K is by far the worst of all of these. But I want to again remind you that the top K performance doesn't have any theoretical backing. So it's really outperforming the best known theory for top K by many orders of magnitude, and people really don't know why it does so well. And this one is still better. And as you go from homogeneous data partition towards more heterogeneous data partition, then the gap kind of closes, and at some point, top K even becomes better. Towards the end, they match again, but they pretty much, I would say, are comparable across the range from homogeneous to heterogeneous. Okay, so I said this, and that's really the end. So I'm quite happy to receive some questions about these experiments, if there are any. And thank you very much for your attention.
Thank you very much. So, are there any questions about the last slides?
If there's nobody else I want to ask, but I don't want to ask too much questions. So.
Please do.
Okay, thanks.
Thanks for the
presentation. I was really enjoying the presentation, and I was wondering, like this improvement does not like rely on like a non-convexity or like whatsoever. I was thinking, can we extend like the similar idea to the, for example, convex smooth functions?
Yeah, so in fact, when we started this project, it started with a result that holds for strongly convex functions. Mm-hmm. So we had that before we even discovered these results for non-convex functions. But for strongly convex functions, you need to work with different algorithms because MARINA is not the state-of-the-art algorithm. But then we thought at some point that in fact what would be most impactful in machine learning would be to study the non-convex regime, which is much more challenging. So then we turned our attention to that, and then we discovered all of these things such as B inequality and Hessian variance and so on. But you're completely right. The idea of correlating compressors and permutation completely is valid also for convex case or strongly convex cases, nothing to do with non-convexity.
Thanks.
Yeah, but the definition of B inequality would, I don't think, would be useful in the strongly convex regime. And I have reason to believe why that is the case. So one would have to figure out the new theory, but the generic idea of correlating compressors would still be there. So one should still correlate compressors somehow.
You mean like in a convex case, we can still maybe use correlated compressors?
Yes, so even permutation compressors. Exactly, the permutation compressor would work, but proof of improvement would not be using the AB inequality. The AB inequality, in some sense, makes sense for certain reasons, which have something to do with the fact that MARINA is a variance-reduced method, which kind of means it works with gradient differences, and that's why it looks like it does, the inequality. So some different inequality would need to be used. But there will still be improvement from permutation, from smart correlation.
And my second question would be very naive, but like, do you think is there any more room to explore other correlated compression? Like permutation was like a very intuitively, beautifully works, and I was thinking.
So that's an excellent question, and usually people say something is an excellent question when they have an answer. So we do have an answer in the paper. So we have many examples of other compressors which are not permutation based, or permutation appears in a different way, which are still input variance compressors. So it's really the general definition of A B inequality and input variance compressor where A is equal to B, which matters, and permutation is just the simplest way of obtaining that. But what really matters is this more abstract notion of input variance compressors. We don't think we discovered all of them, but we have some list of further compressors in the paper.
And in a theory-wise, like because permutation is A equal to B, and like there's no kind of better one in a sense found already.
Yeah, so there's some other compressors where A is also equal to B. So there's some other ones.
But cannot be kind of strictly better than the permutation-based thing.
Well, yeah, well,
perhaps
I don't really
work.
So I don't think we went with the theory so far that we would know that this is really the best approach. It is the best we could think of, but maybe still something else can happen, because A equals to B is really great, because then you get rid of this big constant L plus. But then you would also want the B to be as small as possible, subject to the constraint that A is equal to B, right? Because the B then multiplies L plus minus. And we don't have a theorem in the paper which would say that the best compressor which minimizes B subject to A is equal to B is this. We don't know that. If you can do that, you could probably have a paper.
It probably depends on the function, like objective.
No, this has nothing to do with the objective. This is just property of the compressors. It's nothing to do with the objective.
If L plus minus is 0, like B can be any large. Like if L plus
sure. But if it's not, then B matters, right? So I'm defining optimization problem. Generate compressors such that minimize B subject to A is equal to B. Do we have an answer? We don't. We didn't ask that question, but it's a very natural question to ask. And if maybe permutation compressors are the answer to the question, maybe. I don't know. But if they are not, and there is an answer to the question, I think it would be worth the paper.
I have to study the paper first of all. Thanks.
Okay, thank you very much.
Thanks everybody for engaging with me. I appreciate it a lot.
Thank you so much, Peter, for such a beautiful presentation. And to the audience, we will see you hopefully next week with the next presentation of the online seminar series. Thank you all. Bye-bye.
Thank you. Bye-bye.